Hello and welcome to topic 7, Singularities and the residue theorem. In this topic, we're going to work up to one of the most remarkable and useful results in complex analysis, the residue theorem. This is really one of the big payoffs from all that we've covered so far in the course, and it's a really wonderful result. Now, from the previous video, we know that functions may be expanded in Laurent series about a singular point, where the function is not analytic. And here we're going to be investigating different types of singularities by looking at their Laurent series. After that, we'll then consider integrals of functions around contours enclosing singularities, and this will lead to an amazing result that contour integrals enclosing singularities of the function, the value of those integrals is governed only by properties of these enclosed singularities and not by other details of the contour. This is the residue theorem. In this first video, we'll look at two types of so-called isolated singularities, poles and essential singularities. The Laurent series of a function about a pole truncates at some negative finite power of z. On the other hand, the Laurent series of a function about an essential singularity continues to negatively infinite powers of z. These are the intended learning outcomes for this first video. After watching this video, you should be able to identify different types of singularities, namely branch points that we encountered back in topic 4, and also poles and essential singularities. These last two are characterized by the function's Laurent series in a neighborhood of the singular point. You should also be able to identify and characterize these isolated singularities from the function's Laurent series. In particular, we're going to see that the order of a pole is given by the most negative power in the Laurent expansion. Finally, we're going to look at how to relate zeros to poles of complex functions. And with that, let's begin.
In this video, we're going to be talking about singularities. Let's begin by reminding ourselves what a singularity is. A singular point of some complex function f of z is any point in the complex plane at which the function fails to be analytic. We've seen a few examples of these already. I'll list one here. For example, we have already encountered branch points. In topic 4, when we were discussing multivaluedness. We'll now look at characterizing some other types. That's what we'll spend the rest of this video doing. Okay, let's consider f of z to have a singularity at the point z0. Now this is a bit of terminology coming up next. We call this point z0 an isolated singularity if f is analytic in a neighborhood of z0. I'll draw a picture in a second to make it clear what that means. And I'll highlight this terminology, which is important. Isolated singularity. Okay, so let's draw a picture. So in the complex plane, I'm not going to bother drawing the axes, but we might have the point z0, at which our function f of z is singular. Now I'm going to depict a neighborhood around this point as a disk. So I'm going to label this point is our singularity. And then we have this circle around the point of radius delta. And the region within this circle, excluding the singularity, is the neighbourhood of that point. And we say that z0 is an isolated singularity if f of z is analytic inside the possibly very small neighbourhood of z0. And this is, from this picture, a disk of radius delta that has to be greater than 0. Essentially, this says that as long as we can find a region around this singular point z0, it doesn't matter how small it is, as long as it exists, then we call the singularity an isolated singularity. To make this clearer, I'll give you a couple of examples. First of all, let's consider f of z is 1 over z times 1 plus z squared. You can see that this function is going to be singular when the denominator vanishes, and that happens when z equals 0, or if you factorize the term in brackets, it'll also be 0 when z is plus or minus I. These points are isolated singularities. You could define a neighbourhood like in the picture above. So this function, we say, has isolated singularities at the points z equals 0 and plus or minus I. Let's now look at another example that does not have isolated singularities. Let's consider f of z is 1 over the sine of pi divided by z. Again, we'll look at points where the denominator equals 0. Of course, you'll recall that sine x equals 0 when x is an integer multiple of pi. So m is an integer. You'll spot that for some values of z lying on the real axis, the denominator is going to equal 0, and we have a singularity. I'll draw a little picture so we can see what's going on. We have our real and our imaginary axes. And I'm now going to label the values of z that make our function f of z non-analytic. So if z equals 1, then we have 1 divided by sine of pi. That's undefined. So this value of 1 is a singular point. If z equals minus 1, then we have the same behavior. So z equals minus 1 is also a singular point. If we try z equals a half, then we have 1 divided by sine of 2 pi. That's also not analytic. So a half is also singular. Similarly, minus a half will give the same behavior. And you'll now spot that whenever z is 1 divided by some integer, the function is not going to be analytic. So those correspond to singular points. I'll draw a few more on this picture here. So we'll also have that 1/3 and minus 1/3 are singular. The same for 1/4, minus 1/4, and so on. There'll be an infinite number of singularities tending towards the origin. What does this mean? Well, it means that here, the point z equals 0 is also singular. You can check that by putting z equals 0 into the expression of our function. However, we've just seen that for every choice of delta greater than 0, so looking in some neighbourhood of the point at the origin, you can always find another point z that's not 0 lying within the neighbourhood defined by delta that is also singular. We can always find a large enough integer such that when z is 1 divided by that integer, it lies arbitrarily close to the singular point at the origin. What does this mean? Well, it means that our function f is not analytic in any neighbourhood of the point z equals 0. And that means that this point is not an isolated singularity. We can make a brief note about the other kind of singularity that we've encountered, branch points. Are branch points isolated singularities or not? Well, it turns out that, just like the example we just looked at, the multi-valued functions like the complex logarithm and roots of complex numbers, these multi-valued functions have non-isolated singular points at z equals 0. How can we tell? Well, we can consider the behavior in a neighbourhood around that point. For these functions, any neighbourhood will contain points belonging to a branch cut. You'll recall that we used branch cuts to restrict the input to our function in order to guarantee that it was single valued. And we got single valuedness at the expense of a discontinuity across the branch cut. So as a result, these functions, they are not continuous, and so they are not analytic in a neighbourhood about z equals 0. Oops. Okay, so we've just seen examples of a function with an isolated singularity, and then examples of singularities that are not isolated. There was the 1 over the sine of pi over z, and then these multi-valued functions that have branch cuts. A bit of terminology here. A function with only isolated singularities, like the first example that we looked at. Such a function is called meromorphic. And that's in contrast to the term we had earlier in topic 3, holomorphic, which was another way of saying that a function is analytic. Okay, well, what does it mean if a function has an isolated singularity? Well, we can now make use of our discussions in the previous topic looking at Laurent series. We say that if z0 is an isolated singularity, then by definition there exists a region defined by this inequality, and this is precisely the neighbourhood that we drew in the picture earlier, and this is a region of analyticity of the function. And in fact, this is an annulus of analyticity. That means that by definition there exists a region for which the Laurent series about z0, about the singularity at z0, is valid. That means that we can write our function f of z in a Laurent series, which is given by the sum from n equals minus infinity to infinity of some coefficients and then powers of z minus z0. Okay, so we can expand the function as a Laurent series. Now we can characterize the singularity using its Laurent series in one of two ways. So for the Laurent series, one of the following statements is true. First of all, the Laurent series that we've obtained from our function when expanded about the singularity at z0, the first possibility is that our Laurent series truncates at some negative finite integer. I can write this as there exists some positive integer m such that the coefficient a minus m, so that's the coefficient associated with z minus z0 to the power of minus m, that coefficient does not equal 0. But on the other hand, these coefficients, for all negative n less than minus m, all of those coefficients are 0. Putting that another way, I can say that if the Laurent series truncates at some negative finite integer, it means that m is the most negative power of z minus z0. Such a function would look like this. The lowest term in the Laurent series would be a minus m over z minus z0 to the m. And we can write the other terms in more positive powers of z minus z0. Those coefficients might vanish. The important thing is that a minus m is non-zero. But you notice that all of the coefficients with index less than minus m are 0. If we have a function with a Laurent series like this, then a very important piece of terminology, we say that the point z0 is called a pole of order m. This is very important terminology. We can imagine something like a pole of order m equals 1. That would have an expansion where the most negative power is simply z minus z0 to the minus 1. So there are no terms in 1 over z minus z0 squared, for example. So this is what a function with a pole of order 1 looks like. We call poles of order 1 simple poles. So this function here would have a simple pole at z0. The other possibility for our Laurent series is this. The Laurent series does not truncate. So it doesn't terminate. Instead, it continues to negatively infinite powers. If this is the case, then we call the point z0 an essential singularity. This is another important piece of terminology. And note that we don't call these poles. So quickly looking back at our Laurent series expansion, we have two possibilities. Either there exists some negative finite integer at which the Laurent series truncates, and there are no lower negative powers in the expansion, or the Laurent series never truncates and it continues to negatively infinite powers in z minus z0. We'll now look at a few examples. First of all, let's look at f of z is 1 over z. This is a straightforward example. This function has a singularity at z equals 0, and from our definition above, the most negative power in the Laurent series expansion is simply the term given, 1 over z. That means that we have a pole of order 1 at z equals 0. In other words, we have a simple pole at z equals 0. Let's look at a second example. Let's consider our function is 1 over z minus 1 squared. Well, this function is singular when z equals 1, and in this case the most negative power in the Laurent series is again, as given, 1 over z minus 1 squared. So this is a pole of order 2. At the point z equals 1. What about this function? Well, if we put in z equals 0, then we clearly see that the function is singular at that point. We can use the normal series expansion of the exponential function and substitute in 1 over z to get that this is the sum from n equals 0 to infinity of z to the minus n over n factorial. Clearly this Laurent series does not truncate. It continues to negatively infinite powers of z. Therefore, this function has an essential singularity at z equals 0. To finish this discussion, we'll look at a slightly more complicated example. F of z is 1 over z times 1 plus z squared. Again, looking at when the denominator equals 0, we spot that this function has singularities at z equals 0 and plus or minus I. The crucial point here to characterize these singularities is that for each singularity, we need to expand the function in a Laurent series in a neighborhood of the singularity that we're interested in. This is really important. Let's begin with the singularity when z0 equals 0. Well, actually, in the previous topic, we found the Laurent series of this function in a particular neighborhood about this point. From the previous topic, we have that this region, where the absolute value of z lies between 0 and 1, that region we saw was a neighborhood about this singularity. and we found that the Laurent series about that point of our function was 1 over z minus z plus z cubed, and so on. We can immediately read off from the most negative power in the Laurent series that z0 is 0 is a simple pole. Okay, what about the Laurent series about the singularity at z0 equals plus I? So we're now interested in z0. It's plus I. Well, to find the Laurent series about that point, we're going to let epsilon equal z minus I, and then expand in powers of epsilon. We can write our function as 1 over z times z plus I times z minus I. Substituting in for epsilon, we can rewrite this as 1 over epsilon I plus epsilon 2I plus epsilon. We can start tidying this up to make it look like geometric series that we know how to treat. We can write 1 over epsilon times, and then we take out a factor of I to get 1 plus epsilon over I. And then that last term we're going to take out a factor of 2I. And in the brackets we now have 1 plus epsilon over 2I. You'll recognise the two terms on the right hand side as the limits of complex geometric series. We have 1 over epsilon times 1 over I, the sum from n equals 0 to infinity of minus epsilon over I to the n, times 1 over 2I, the sum from n equals 0 to infinity of minus epsilon over 2I to the n. I'm now going to take the leading terms in these expansions, because that's all we'll need to find the most negative power. And this is going to give us 1 over epsilon times I times 2I. And then this first infinite series, we're going to take out 1 minus epsilon over I. And then there'll be terms in epsilon squared. And then this second infinite series, we're going to take out the n equals 0 term, the n equals 1 term, and we note that the next order terms are going to be in epsilon squared. Now I'm not going to go through the next step explicitly, but you can then write this as minus 1 over 2 epsilon plus 3 over 4I plus terms of the order epsilon. I encourage you to try this step yourself. Finally, we're going to substitute back in for z. We have that epsilon is z minus I, and so we can write this as minus 1 over 2 lots of z minus I plus 3 over 4I, and then plus terms of the order z minus I. That means that we can read off from this first term that z0 is plus I. That singularity is a simple pole, because the most negative power is z minus z0 to the power of minus 1. And you can check for yourselves, but this turns out to be true also for the other singularity at z0 is minus I. Okay, so that's it for some examples. Next, note that a pole of finite order M may be removed in the sense that if f of z has a pole of finite order M, then the new function we define g of z as f of z, the one with a pole of order M, but then multiply by z minus z naught to the M, well, this function is going to be analytic. That's easy to see from the Laurent series. Essentially, multiplying by z minus z naught to the M removes all negative powers in your series expansion, and so you recover a Taylor series for g of z, which makes g of z analytic. I'll note that an essential singularity cannot be removed in this way. A useful trick to identify poles of functions without expanding in a Laurent series, I'll say that a way of identifying a pole of f of z without its Laurent expansion is to examine the following expression. The limit as z tends to z naught of z minus z naught to the n times f of z for various positive integers n. Okay, so if you construct that expression and take the limit as z tends to z naught, then it turns out that the smallest n for which the limit exists, and is finite, that then gives the order of the pole at z equals z naught. For essential singularities, this expression won't converge for any finite value of n. The last point I'm going to make in this discussion about poles is how to look at the behavior of singularities at the point infinity. You can check behavior of some function at infinity, and this is similar to our treatment of behavior at infinity for multi-valued functions. You set zeta is 1 over z and look at the behavior of f of zeta at zeta equals naught, because then that tells you the behavior of f of z at z equals infinity. For example, consider f of z is z times 1 plus z. Well, if we perform that substitution, we have that f of zeta is 1 over zeta times 1 plus 1 over zeta. Multiplying this out, we have 1 over zeta squared plus 1 over zeta. And you can therefore spot that this has a pole of order 2 at zeta equals 0, which means that f of z has pole of order 2 at z equals infinity. And in fact, many functions that look analytic have singularities at z equals infinity. I'm going to end this video with a quick discussion about zeros of functions. And this is a quick aside to link zeros of functions to the poles of functions. What is a zero? Well, zeros of some function f of z are points, let's call them z0, where the value of the function equals 0. So these are inputs that produce an output of 0. We can characterize zeros in this way. A 0 is of order m, which is a positive integer, if the function value at that point vanishes, and also the first derivative and all of the derivatives up to the m minus 1th derivative evaluated at that point z0, those all vanish as well, but the mth derivative is not 0. Putting this another way, we say that the first non-zero term in the Taylor expansion is Pm z minus z0 to the m, with m as a positive integer. You'll recall that Pm are given by the mth derivative evaluated as z0 divided by m factorial. And we name these in a similar way to poles. We say that a 0 of order m equals 1 is called a simple 0. Let's look at a couple of examples quickly. If we have f of z is z, well, that is its own Taylor series, and we see that the first non-zero term is z to the power of 1. That means that this has a simple 0 at z equals 0. What about this one? Z minus I squared. Well, we can see that this function vanishes at z equals I, and by the fact that this is its own Taylor series, we can identify that as a 0 of order 2 at z equals plus I. A couple more quick examples. F of z is z squared minus 1. This function has zeros when z squared minus 1 equals 0. So we can note that this has zeros at z equals plus or minus 1. To characterize them, we have to form the appropriate expansion. If we consider about z equals minus 1, then we can rewrite this, and you can check for yourselves, as z plus 1 squared minus 2 lots of z plus 1. And the first non-zero term in this Taylor expansion is minus 2 lots of z plus 1. So this is a simple 0. You can check for the same behavior about z equals plus 1. For our last example, to see how to use the series expansions of known functions. Let's consider z squared e to the z. This has a 0 when z equals 0. Substituting in the expansion for the exponential function, we can rewrite this as the sum from n equals 0 to infinity of z to the n plus 2 over n factorial, and that will give us z squared plus z cubed plus z to the 4 over 2 factorial, and so on. And the first non-zero power is z squared. Therefore this is a 0 of order 2 at z equals 0. And if you want, you can check the derivatives required for the Taylor series explicitly, and you'll find that the first derivative vanishes at z equals 0, but the second derivative does not. The very last point I'll make in this video is that if f of z has a 0 of order m at z equals z0, then 1 over f of z has a pole of order m at that point, and vice versa. So that gives you an idea of the link between zeros and poles of a function. That's the end of this first video of topic 7. As a quick recap, we looked at singularities, and in particular the example of poles. A pole of a function is related to finite truncation of its Laurent series when expanded about a singular point. We looked at ways of identifying a pole's order, and looked at its behaviour at infinity. And we finished by comparing poles to zeros of a function. You'll get lots of practice at finding poles of functions in the problem sheet. Next up is the second video of topic 7. Thanks for listening.